All right, so looking at that circuit, it says use Kirchhoff's laws to state the relation between currents I1, I2, and I3. If we look carefully at this part of the circuit, we can see that I2 is going this way. The current is going this way, and so it would kind of get recharged through the battery, go up here. So I2 is going like this. And we can, if we sort of focus on node B right here, we can see I1 and I2 are going into it, and I3 comes out. So think about Kirchhoff's first law that says the sum of the currents entering into a point, in this case, point B is the one that we're really focusing on, is equal to the sum of the currents coming out of that same point. So the currents going into B are I1 and I2. I1 plus I2 equals the current coming out, I3. I1 plus I2 equals I3. That would be the relationship between the currents in the circuit. I1 plus I2 equals I3. The next one says use Kirchhoff's laws to state the relation between E2, R, I2, and I3 in loop BCXYB. So loop BCXYB is this loop down here, and it looks like we've got Kirchhoff's second law at work now. So it says the sum of the EMFs, which is this EMF, right? That's the only EMF they ask us to consider here. So the sum of the EMFs is equal to the sum of the potential differences. And along this loop, there's going to be a potential difference across this resistor and across this one, right? So there's two potential differences that we must sum. E2 is the only EMF, so the sum of the EMF is just E2, and it must equal, let's kind of follow the circuit around this way. I3 is going across R. Remember that voltage is equal to I times R. And so they don't allow us to sort of write it in terms of voltage. We have to write everything in terms of E, R, and I. And so some of the voltages, the sum of the potential differences is I times R. So this is I3 times R, right? That's that one right there, I3 times R. And then there's another voltage drop across this resistor, but you can see that like when I3 gets to this node here, then I1 goes back up this way, right? It's kind of like if both I1 and I2 go into this point and I3 comes out, once I3 gets here, well, we know I2 is going this way, right? Like this loop contains the current I2. This branch contains I3, which is the sum of I2 and I1, right? And so I1 must be coming out back out this way. So here we don't have the same I3, but we've got I2 going through R. And so the voltage drop across that one is the different current I2, but the value of the resistor is the same R. And so that's your equation for part 2 here. E2, EMF here, equals the potential differences across here and across here. And note that it is the current that sort of is driven through the resistor. That's why I3, goes to this R and I2. The last one says between E1, E2, R, I1, and I2, okay, and just this outer loop. So we don't need to consider sort of this branch anymore. We're just doing sort of the outer loop. When EMF sources are wired like this, with the polarity sort of positive connected to positive, the rule is we subtract the EMF, okay? That is an essential idea that I try to emphasize with the potentiometer circuit, right, where the EMF of the unknown cell has to be wired this way, okay, because we're sort of like canceling out the potential difference. So we're sort of canceling out its EMF as the voltage drop across the potentiometer wire. So here's the left side of the equation now, E1 minus E2. It's in general the sum, but we're like adding the negative, okay, EMF of this one. And then now we just have to kind of follow this circuit around. I'll start at E1, and it's going to go I1 times R. Okay, so now the sum of the potential differences are going to be I1 R. And then if we go down here, we can see that I1 is also going through this R, right? It doesn't matter what order we sort of sum these in. So if we sort of follow all the way around, this is a little bit trickier because look what the current's doing. It's going the opposite way. But here, the current's sort of going this way. And so we got I1 again times R. Right? So the same current I1 goes through both of these resistors here and here. We've also got a negative I2 going through a resistor right down here, right? And so it's like I1R, negative I2R, I1R again, okay? The direction of the current in this bottom loop opposes the direction of the current here, so we need to account for that thusly. So this equation right here would be number 2, right here. And this equation, E1 minus E2 equals, you can combine these. 1 I1R plus another 1 I1R would be, let's just write it in its whole entirety. E1 minus E2 equals 2 I1R minus